All right, so this is designed for Physics 1112, second semester, algebra based. So today we're going to look at, or in this lecture, I should say, we're going to look at current. But the chapter 20, is going to cover current, Ohm's law, resistivity and resistance, electric power and energy, alternating current versus direct current, and then finally electric hazards to the human body. But for now, we're just going to talk about current, and then we will get on with the rest of it in a bit. So let's do that. So let's start talking about current. Current is the symbol that we use for current is I, right? And really all it is the charge per time, right? And delta, you guys know anything delta is delta, the final thing minus the initial thing. So if you're dealing with a certain amount of charge, it would be delta Q, and then a certain amount of time, delta T. So you take that charge and divide it by the time, and you have your current. Now, the units on that, you can see here, we've got our units. It's coulombs per second. Sorry about that. Coulombs per second. So we have this new thing. 1 coulomb per 1 second is an amp. And ampere. There's a fellow named, I don't know his other names. Anyway, his last name's Ampere, right? And we wanted to honor Ampere with the unit for current. He did a lot of work with that. You might also see it as written as 1A. Well, it turns out that charge, the Q, is not the measurable thing. Its charge is not measurable. What is measurable is current, okay? So we can measure current, and we can measure the time. We talked about this earlier in the semester, because last semester we could measure length. What was it? What were the things that we could measure? We could measure length in meters, and we could measure time in seconds, and we could measure mass in kilograms. Well, now we can measure current, and that's in amps. So they're not equal. These are the units, okay? But you would think that charge would be the thing that was measured, but it really isn't. We can measure the current. We can measure the time, but we cannot measure the charge. So what we do is we calculate the charge. And when we go to do that, we use this equation. Okay, we have some measured current, we have some measured time, and we figure out how much charge. Okay, so let's get talking about what does current move through? Well, it moves through a wire, right? So we're going to move our current through a wire, and we know that the electrons, we've talked about this, the electrons are the things that are moving, right? But Benjamin Franklin got us thinking that a positive thing was moving. And so we do this with our current. If the electrons are going one direction, our current's going the other direction. And we would say then that the charge is positive. So it's a positive Q. And it goes through a certain area. And if it does that in 1 second, a whole coulomb in 1 second, that is 1 amp. Now don't worry about how fast these things are moving, because just like in fluids, the less area that they have to move through, so if it's a smaller area, their velocity increases. So we get a conservation of charge, right, through a certain region. The amount of charge, oh, that wasn't very good. the amount of charge that goes through this region from there to there is the same that would go through, say, some region like this from there to there. So the velocity is much less than the velocity here. So V2 is larger than V1, and we'll look at that a little bit later, but that just comes from the conservation of charge. So I keep erasing things. Conservation of charge. Okay, so let's talk about this. We learned that in a conductor, the E field is 0, right? We look at a conductor and we want to know what the E field is on the inside of the conductor, and it's 0. So wire charge is moving. Well, it's because we apply a voltage, all right? So we say, oh, well, you know what we want to do? We want to apply some voltage. So at this side, we've got voltage B. Over here, we've got voltage A. And there's a difference between the two sizes. That's a potential difference, okay? Just like height differences or elevation differences on a topographical map, we now have a potential difference between, and it means that the charges, if they're negative, want to get moved toward the positive side of the E field, and if they're positive, they want to get moved to the negative side of the E field. So that's what happens. All we're doing when we put a potential on something is we're adding an E field to the situation. Okay, that's all we're doing. So let's talk a little bit about copper wires. Copper has an extra an extra electron for every atom. And there's not a lot of resistance. There's some resistance, right? But compared to rubber or something, there's not a lot of resistance. So let's look at the analogy between our E field and gravity. Okay, so what do we have? We've got this little guy right here. That's this guy, and that's a massive, we'll call it a ball bearing. Okay, it just has some mass, and mass times gravity is going to pull that little guy down through the oil. Well, we also have an E field and some charge here in a wire. Okay, it's a copper wire. So this guy is also going to interact with the E field, not the G field, but the E field, and it's going to want to go down the electric field as well. So both these things are wanting to move down because there is a field that's applying a force on them. All right, and we talked about the force and how that force is equal to the charge times the E field, okay, in electromagnetics. Over here, in gravity, we know that it's just our mass times gravity, and whatever the gravitational field is at that point. If you're on the moon, of course, it's going to be a lower G, right? Or if you're on the sun, it'll be a bigger G. When you're moving through something, so we're moving through a wire or we're moving through oil in a gravitational sense, there's friction, okay? So what about this friction? So we've got friction, and that's slowing us down. And we all know if you drop a rock over a bridge or whatever, for a while it accelerates, but it quickly gets to a point where it's not going to accelerate anymore. And that is what we call terminal velocity, right? So terminal velocity happens fairly quickly. In oil, a ball bearing will quickly get to terminal velocity fast. And once it gets to that terminal velocity, then it will stay there, right, until some other force acts upon it. So what does that mean? Well, if it's at terminal velocity, then delta V, that's equal to 0. And if delta V is equal to 0, then that forces A to be equal to 0. So our acceleration is equal to 0. And we've got our sum of the forces in both directions equaling out. So our force of friction is balanced out with the force that's driving the particle through. Well, electrons have this happen to them, and electrons have this terminal velocity, but for electrons we call it a drift velocity. We don't call it the terminal velocity. It's just because the two things were developed separately. So why is there a drift velocity? Because there's some average velocity that things are traveling with. Okay, so the average velocity, because it's this charge is bouncing around like a Plinko machine thing. All right, let's just think of it as an electron. So this little guy here is an electron, and it's going to be bouncing through, just like a Plinko game, bouncing through all of the atoms. Sometimes it hits hard, sometimes it doesn't, sometimes it slides right by other atoms. So all in all, it has some movement. It's going to go in, overall, it's going to go in a certain direction, but that is the average velocity that it's going to go in. Okay, so eventually it's going to go down, or in our case, down. It doesn't have to be necessarily down, but it's going to go that direction with some average velocity, and we call that average velocity the drift velocity. And it also happens to be a thing that it can't really go any faster than that. That's as fast as it gets to go. So, okay, so let's do a little example. How much current do we measure if 720 coulombs of charge are moved in 4 seconds? So we just do it. We plug in our delta Q, 720, we divide by our 4 seconds, and we get our 180 amps. Okay, so that's pretty easy. How long does it take to move that one coulomb of charge through a calculator that has a current of 0.3 milliamps? All right. Well, we just redo the equation. Instead of I equals Q over delta T, we're going to say that delta T is equal to delta Q over I. And our delta Q is this 1 coulomb, and our current is 0.3 milliseconds, or milliamps. Oh my goodness. And so that's here. And then I'm taking this, and it's in the denominator, so I'm putting it in the numerator, and that leaves us with 3.33 times 10 to the third seconds. Well, that's a lot of seconds. That turns out to be very close to about an hour. You can figure out how many minutes it really is, but it's about an hour, and it's 3,330 seconds. Okay, so that's how long a calculator takes to move this amount of charge if its current is this big. And I think a lot of the modern calculators, the current is quite small compared to that. How many electrons then pass through All right, so, well, what do we have to do? We have to figure out our electrons per second. But if you notice, electrons per second is just charge per second, and that's current. Okay, so we have our current, and we know that our current is 0.3 milliamps. And if we have that's coulombs per second, then we can say, oh, well, that's cool, but every coulomb has one electron is 1.6 times 10 to the minus 19 coulombs. So then that means we can just take our current, divide it by 1.6 times 10 to the minus 19, and the coulombs cancel, and we're left with the electrons per second. That is 1.88 times 10 to the 15 electrons per second. So it's a lot of electrons per second, but, oh, excuse me, electrons are so small that, that doesn't really add up to very much. So that's kind of nice. All right, so let's get back to our drift velocity. So what's happening with drift velocity? We have our electrons, they're going in one direction. And what we say is that drift velocity for the electrons is this. Okay, so the electrons are going this direction. The drift velocity for what we call the positive charges that are going in the other direction, let's deal with that right now. Actually, what is the current? What is actually flowing? Well, it's not the electrons. We know the electrons are going the other direction. So what do we have? We have things that we call holes. Okay, holes. So the hole is just like it's an opposite of the charge going in the other direction. Okay, so it's going in exactly the same speed, the drift velocity, but it's moving in the opposite direction. Okay, so we call those holes, and they're moving in the direction of the current. So, which is a positive charge, which means if it has an electric field going in that direction, the positive charges want to go the same direction as the electric field. So that is what we call current. It's just the opposite of positive charge. It's just you just take the positive charge and you make it negative to get the negative amount of charge. So let's say we have a certain area of a wire and we have a certain length of the wire. If we want the volume for that wire, then we can multiply the area times the length. And our area, in this case, it's a round wire, so it's going to be pi r squared. So then our volume is equal to the length times our pi r squared, or pi r squared L. If we define a thing called the density of charges, it's the number of charges of a certain size in that specific volume. And the charge size can be anything. It could be 1 electron. It could be a whole Q of, like 0.3 microcoulombs or whatever. It could be a lot. It could be a little. It doesn't matter. So we just say, oh, well, what is our density of charges? Well, it's the number of charges. All right, that's NQ. That's the number of charges. And divided by the volume. And our volume we just calculated was pi r squared L. So we take the number of charges, we divide by pi r squared L, and that gives us our N. But we're often looking for NQ. We're really wanting to know how many charges are there, right? That's what we're looking for a lot of the time. So to do that, we take our N, our density of charges, we multiply it by the volume. Our N times the volume, that's going to be our number of charges. Okay, so if we take the size of each Q, here's the size of each Q, we multiply it by the number of them, and we divide that by our time that they travel through a certain region, then we basically have our current. It's how much charge goes through in that certain amount of time. So where does that get us? That gets us our Q times the density of charges times the volume divided by time. And if I rewrite it, I can put all of these things in front and have our ratio be our length divided by time. Well, what's length divided by time? That's a velocity. So our velocity is multiplied by our density of charges. Oh, I dropped a Q here. We need a Q in there. Oh, let's figure out how to get a Q in there. Our Q times N times, oh, I don't want that. I want an area. Okay, sorry about that. So we've got our charge, we've got our density of charges, we've got the area of the wire, and then we've got our velocity, drift velocity. And that's our current. And that is a very important equation to keep in mind for the homeworks. You'll want to know that. So I just rewrote it here. And you'll notice that the VD, that's our drift velocity through the area. Our Q is the charge size. Our N is the number of charges. And then, of course, the area is the cross-sectional area of our wire. So an example. Now, this is a little bit complicated. Example. We want to calculate the drift velocity for electrons moving through 12-gauge wire, okay, and it carries 20 amps. So our wire is copper, and we're given that the density of copper is 8.8 times 10 to the 3 kilograms per meter cubed. We also know that each copper atom has a free electron. So that is a free spirit, basically. And the periodic table says that copper weighs 63.54 grams per mole. Okay, now we're basically trying to figure out drift velocity for each of the electrons. Okay, so we really got to get down to the electron aspect of this. So how many atoms in a mole? It's 6.02 times 10 to the 23, Avogadro's number. So 1 gram equals 10 to the minus 3 kilograms. We know that. All these things are going to go through and figure out how many electrons per meter cubed we've got. So we have our mass, all right? We've got, that's this, whoa. We've got our mass. That's this guy right here. We know there are 10 to the 3 grams per kilogram because we got to get rid of kilograms. we've got 6.02 times 10 to the 23 atoms per mole. So that's good. We've got 1 mole is equal to 63.54 grams. So our grams can cancel, our kilograms can cancel, our atoms can cancel because 1 electron per atom. Our moles cancel, and we are left with electrons per meter cubed, and that's exactly what we want. We have the number per volume of electrons, and that's 8.34 times 10 to the 28 electrons per meter cubed. Those are free electrons ready to go. Move around. So if we use that, and we use this equation right there, we can then solve for the drift velocity. So our drift velocity is equal to our current divided by our charge density times the charge times the area. So all that stuff is in the denominator. If we do that, we should get a nice little number. Let's see about that. So our drift velocity. You got to define a coordinate system. There's just no way around it. So my coordinate system is here, okay? I'm saying to the right is positive, and my electrons are moving in this direction. The current is going in the other direction. So when I say that I've got negative 20 here, what I'm saying is, sure, it's a positive magnitude, but it's negative because it's going in a certain direction. So the direction tells me that that's negative. But also down here, when I go to put my charge, I put my charge in, it's a negative electron. So those two things are going to cancel out, and the negatives cancel out and leaves me with a positive number. So now I have to ask myself, is this really a positive number? Well, yeah, it is, because to the right is positive, and my drift velocity is positive. These little electrons are going in the positive direction. Now, the one thing I didn't talk about is our area. And why is our area the way that it is? Well, area is equal to pi r squared. We already talked about above that there's some millimeters, 2.053 millimeters is our diameter. And if we take our radius divided by diameter is equal to our radius divided by come on, dude. Our radius is equal to our diameter divided by 2. So when I insert the radius, I'm going to insert that and I'm going to make it squared. Well, what is that? That's our d squared over 4. So that's where the 4 comes from, and it's simple. We convert the millimeters to meters. That's this number. We square it. We get a really small number, divide by 4, even smaller, and then multiply by pi. That leaves us with this amount of area. So we plug that in here into our area and go, right? We've already done this. That was the hard part. The rest of it's fairly easy, and we get this drift velocity. And we know, using our coordinate system, that it's a positive drift velocity. All right. That does it for current. In our next lecture, we're going to start talking about resistance and Ohm's law. And here we go. So we're going to start here with resistance. Boy, that didn't work. All right, well, I'll have my stuff together for the next lecture. So thanks for paying attention.